And now let me give you a simple derivation of the plasma sheath. So we have the electron density with the Boltzmann distribution, and based on the conservation of energy, this is where in the center. Inside, this is where the velocity in the a little bit outside is a finite electrostatic potential, and it's due to the conservation of flux. We have this combine those two equations, we'll end up having this equation for density of ion. And using Poisson's equation, we plug into equation 1 and 2. We have this expression. This expression is basically the nonlinear expression for the plasma sheath. To calculate that, I suppose you could, for the given profile, you could do some numerical calculation. But for us, let's just linearize it for the sake of analysis. Of course, as we know that the E5 over TE is much less than 1 is not valid at sheath. But for the sake of argument, let's just use this approximation, and we ended up getting this. And then we use the definition of the wavelength to get this expression. Use the definition of speed of sound, square root T over mi. We get this. And the definition of Mach number is V naught over basically how many speed of sound in the medium is for the flow of velocity. And then we get this expression, which is a linear expression for this. And we can see that is not dependent on the location here, so it's only 5. Then that means we have general expression in this way. And of course, for oscillatory, for this less than 0 or m greater or equal to 1 supersonic, we have phi being oscillatory, and they have a plus-minus solution, of course, and less than 1. Due to the boundary condition constraint, we only have a decay expression, and they will be looks like this, as I showed in the physical understanding video.